Well, hi everybody. Good to see some old faces, some new faces. Tech people may still be coming in, so I'll get going here. So my name is Armando Casillas. I am a former egg student, so I was part of the first cohort. How many of you guys are eggs besides the ones that I already know? Any other eggs? So very nice to meet you. Very nice to meet you. So yeah, I was a former egg for our first cohort. I graduated in 2019 with a master's in energy systems. Did a lot of my research out of the Western Cooling Efficiency Center. I spent a lot of my time there getting my thesis done, and I work for Lawrence Berkeley Labs. Been there for 4 years, and you know, as you guys know, the pandemic is very weird for a number of reasons, and we had a very, I think, solid pipeline of talent, people, you know, a lot of like really strong connection with UC Davis. Myself and my supervisor who's going to be presenting today are also from UC Davis, so there's a strong connection, and I thought it'd be good to kind of come in person and kind of reestablish things, get to know some new people, put faces to names, you know. And anyway, I'm really happy to be here. And yeah, this is my presentation. It's enabling decarbonization of buildings through optimized control of electrified loads. So like 4 or 5 different buzzwords all put together. It was mostly put that way so I could keep the topic open and put slides together later on after I submitted this. So anyway, so a little about LBNL. Lawrence Berkeley National Laboratory is a national laboratory and located in Berkeley, California. We're primarily funded by the Department of Energy. We also have some state funding. The State Energy Office, California Energy Commission provides us funding as well. I'll talk a little bit about a project we have with them. And we also get some funding from the investor-owned utilities like PG&E, SoCal Edison, SDG&E. We have concurrent projects with them across our different divisions. I work for the Building Technologies and Urban Systems Division, which is BTUS for short. The non-SI unit for heat, basically. But we work a lot on energy management and information systems, data analytics related to buildings, as well as how to enhance operational efficiency of different facilities management teams. So it kind of cross-cuts between technology, data science, and also kind of social science as well. We work a lot on controls, integrated systems of building automation, semantics, interoperability, something Marco will talk about in a little bit as well. And we also develop simulation tools for Modelica, popular tool like Energy Plus that was developed by NREL, a very popular building energy modeling tool. So yeah, this is kind of an overview of what we do at BTUS. So obligatory duct curve slide. Do I need to go over this? Everyone's good on this one? I can just skip over, okay. A lot of renewables. We need to kind of fill the duct curve. And we do a lot of that with building flexibility, which I'll talk about a little bit here. So buildings are a big contributor to energy use across the nation, across California, primarily through HVAC systems, having to heat outside air, dehumidify, cool the air, and more recently with the pandemic, having to filter out airborne illnesses. A lot of the guidance for air changes per hour is a lot higher than it used to be, which also contributes to a lot of energy use. So the big thing here, though, is with this recent push for electrification, buildings are going to have to also accommodate space heating through electricity, which causes more stress on the grid. So this is kind of where the GEV initiative comes in, right? So the GEV initiative was adopted in 2019, basically trying to remake buildings not into energy efficient resources, but also demand flexible resources. So being able to enable technologies to communicate with the grid in a way where they're able to respond and modify the way they use their load to accommodate the grid's needs. These are called kind of like non-wire alternatives, which are projected to save the US power system about $100 to $200 billion over the next 20 years, which is pretty significant, and also help decarbonize the grid. I think it's 80 million tons of CO2 by the year 2030. So GEV is a kind of a big guiding message, guiding kind of mission for a lot of the research we do at the lab, and some of what I'll talk about today as well. So we talked about GEV and how that kind of guides us and some of the different projects I'll be talking about today, and as well as a lot of the CEC, stuff that we do nowadays is revolved around CalFlexSub, which I'll also talk about. So this is just an overview of how GEV kind of is integrated through a lot of the different projects that I work on and Marco worked on as well. So CalFlexSub is kind of the marquee right now CEC project that the lab is working on. Not just the lab, DC Davis is also involved. A lot of different stakeholders involved in trying to advance the capability of buildings and end uses to be able to be more price responsive, right? So the idea would be to not just create end uses that are able to respond to a dynamic price or TOU price, but also develop the logic for a lot of the end uses, and also develop a standardized way of getting a price signal to these devices. We call it, prices to devices as kind of like the quippy sort of concept here, right? So the idea is to develop these control logics, standardize these price signals, kind of unite those price signals with the devices, and develop control logic for a series of devices. So on top of prices as well, we're also integrating greenhouse gas signals as well. So the idea would be you could either take a price signal or a greenhouse gas signal and optimize your operation based on that. So in terms of standardizing price signals, we used a sort of CalFuse-like approach that is trying to emulate more of a dynamic price signal. So the one you see here kind of highlighted is a two-peak highly dynamic price, which is something you see around this time of the year, right? More of like a duck curve shaped plot. Something you'd see in the summertime looks more like this, where you'd have a lot more stress in the evening. Once the sun goes down, people are coming home, a lot more cooling load, and then your kind of standard TOU shaped price signal, right? So these are price signals that we standardize, we package, and we're actually able to send out through mechanisms such as the CEC MIDA server, which also handles greenhouse gas signals, and our internal CalFlexSub server. So the idea would be that each individual project would be able to get sort of API or something to connect the price signal to whatever they're working on their logic, and actually actuate differences in behavior based on that price signal. Right? So in terms of electrification, right, I had all these buzzwords. Two technologies I'm going to be talking about is our heat pumps and phase change material thermal energy storage. So heat pumps are an electrified means of space heating. Basically kind of reversing the refrigerant flow to expel heat into the space as opposed to in the atmosphere, right? Phase change material thermal energy storage is something you'd integrate with something like a heat pump, and also allows for enhanced load shifting. Phase change material can be, the chemistry of phase change material can be made in a way where it can melt at different temperatures. So the idea would be that you could have a phase change material for like a really high temperature to kind of accommodate space heating, and a really low temperature PCM that could accommodate something for space cooling, right? So, yes.
What is that thermal energy storage? What is it made of?
It could be made out of a lot of different things. I've seen some made out of like paraben wax, salt hydrates, just all kinds of different stuff that kind of solidifies and melts at different temperatures. So I like to think of it kind of like what you get out of like you ever got hurt, you get one of those like ice packs full of like weird gel stuff, right? It's like it melts at certain temperatures. It can melt at colder temperatures to provide something that's colder than water that kind of solidifies at 0 degrees Celsius. So, I have two different projects to talk about today, both related to those technologies I just mentioned. So this is one CEC funded project called HP Flex, where what we're doing here is developing an optimized control system to deploy into buildings that have rooftop heat pump units. So I talked about this kind of electrification of space heating. Once looking in the future, once we have a lot of heat pumps on the grid, we'll have to accommodate and coordinate these heat pumps to avoid causing a new kind of morning peak, we call it, right? So like when all these systems are turned on in the morning, people are coming into the buildings or turning on the thermostats. All of a sudden, we're going to have a new peak in the wintertime that's kind of associated with all these heat pumps that we're putting online. So we're kind of getting ahead of the game and starting to develop a way to kind of coordinate these systems, get these systems to be more price responsive through something called model predictive control. So model predictive control is also kind of like a little bit of a buzzword, but it's a means to be able to predict in the future thermal loads and optimize the operation of a system based on some sort of cost function. So a cost function could be minimizing electrical costs, minimizing greenhouse gases, whatever your target is. The optimization algorithm will kind of modify the way the system is used to kind of meet that goal. So part of this project is developing the MPC for kind of a standard heat pump RTU system with a accompanying building, developing a middleware that connects the price signal that I talked about earlier and the actual control logic that's being implemented into the heat pump system. And all of this is being developed so we could deploy this technology in 6 buildings across California for this project called HP Flex, including the Western Cooling Efficiency Center. I've been talking to Fred about getting this into their building, 2 Bay Area churches, 2 community colleges, 1 in LA, 1 in Bakersfield, and an LA library. So we're actually funding the replacement of their system to the heat pump. And on top of that, overlaying that control system to demonstrate this. So we used FlexLab, which is our sort of crown jewel at the Building Technologies Urban Systems Division. It's the state-of-the-art test bed that allows us to kind of simulate a lot of real building scenarios. So I like to kind of highlight this kind of identical cell, like side-by-side cell scenario, where the idea would be that you could have kind of business as usual case in one of the cells, and then a test case in the other cell, and really kind of measure in real time the difference in behavior, difference in performance of the test cell based on the baseline, right? Everything in the front, all the facade is interchangeable. We could also do some interchanging of the HVAC system, what's conditioning the system. We have these occupant simulators that you've probably seen that just output the same heat that a human would output in a building to really simulate the internal loads that you get in the space. And also thermal comfort stations to make sure we're kind of assessing how comfortable that space would be for an occupant. And anyway, that's kind of been our team's kind of playground the last couple of years. It's fun a lot of time, but also it can be really frustrating and just a lot of time sunken into developing tests for FlexLab, but it's very useful for us. This is kind of an overview of what we did here for the HP Flex. We developed this MPC algorithm. A big part of this MPC algorithm, as I mentioned, is the ability to kind of predict the load in the future. One input to that is outdoor air temperature. The other input to that is kind of predicted internal loads, how the space kind of responds to thermal loads, developing what we call a system identification strategy. So perturbing the FlexLab in a way where we could develop estimations for things like capacitance of the building, resistance of the building to build a kind of reduced order model for the MPC. We have that standardized price signal that I talked about. So all that is unified into the middleware that we developed as part of this project and then deployed in the FlexLab. And what we do basically, yes, go ahead, Dr. Kasich.
Go ahead and finish your sentence.
Okay, so basically what we do here is we change the way that the set points are scheduled in the heat pump system, so we could preheat, get some of that electricity demand at earlier times to avoid kind of a high price period of the price signal. But go ahead, Dr. Kasich.
So you mentioned the heat capacity of the building and stuff. It's I was thinking of the effective heat capacity. Is that a number you put in, or is this something that is learned by looking backwards and seeing when the heat goes on, how long it takes the temperature go up?
You could definitely use historical data, and I think that was an input, at least initially. But given the fact that we have a test bed where we can actually just actively perturb the system and run scenarios that you wouldn't normally be able to run in a building, we were able to more accurately represent the capacitance resistance of the FlexLab itself through that process.
By a calculated number?
So basically, like you said, you turn on the system for a given period of time, you see how quickly that temperature goes up, knowing the other internal loads in the space, estimating solar heat gains, things like that. And you'd be able to kind of isolate, yes, kind of a single number or something that would.
But you did that, then you did it empirically, but you did it as an outside analysis and came up with the effective essential capacitance and put it back in.
Exactly.
You didn't just write a learning algorithm that over time would look back at this and find it.
Yeah, I think it's definitely the former. There's more seasoned MPC experts in the room that can maybe talk about different flavors of MPC, but I think it was definitely more of let's perturb the system and estimate values for the reduced order model. Yeah. So anyway, so this is kind of how we use FlexLab to develop the HP Flex software. We ended up testing this MPC and found that we were able to. Yes, go ahead.
But you've got a hand up one.
Oh yes, Marco, go ahead.
Oh, well, sorry. I wanted to answer the question that, yeah, as you said, there's different flavors. The simplest one is you learn these parameters once. They're different for each building. The structure of the model is the same, but the values are different. Or you can have what's called adaptive MPC, which is basically continuously or periodically updating those values.
Thanks, Marco. Right, so I'm gonna kind of breeze through these because I feel like I'm spending a little too much time, but we basically ran MPC, mentioned, you know, having a baseline scenario in one cell and another scenario on the other cell, and we were able to show that with this MPC, we're able to shift load from high price period to the low price period to reduce around 30% of the electrical demand, and kind of create cost savings that way in a simulated sense. We did test two different flavors of MPC here. One is an ideal MPC where you can actually have the internal gains of the space as an input, and the other one where you're actually estimating it using a black box, gray box approach. And at least in the peak reduction category, they were pretty comparable. The thing about that is when you're trying to deploy this stuff in the real building, you really don't have those values. You don't have internal gains. In FlexLab, we know exactly what those values are because we're turning on the occupants, right, and turning on the plug-web simulators. So we know those values, but in the real building, we won't. So a hybrid MPC is something that'd be more scalable out in the field. So these were encouraging results here.
Sorry.
Yes, go ahead.
So interesting too. So you didn't have phase change material or thermal mass,
Nothing.
you know,
No.
external thermal mass. So basically, you let the temperature float, right,
Mhm.
to shift it. And how far did you let the temperature go down or up, you know, to shift these loads?
So in this particular case, we preheated to somewhere around, you know, like 74, 75. And just at that point, once that peak price period hits, you just let it float, like you mentioned. And you just like the temperature is going to kind of coast down to a point where it might need heating again, might not need heating, depending on what's going on. The cool thing about morning warm-up, however, is that you kind of preheat, right? And then you're kind of also allowing the solar heat gains to help you out, kind of take over. So this ability to preheat is I think a little more practical than something like a pre-cooling strategy where you're kind of fighting against the kind of ever-changing conditions of the space. So yeah, precisely that. Just preheat to 74, 75, and then let it flow from there. Yeah. So this is the second project I wanted to talk about. This is a DOE funded project, or was a DOE funded project, where we're looking at integrating phase change material, thermal energy storage into an air-to-water heat pump system. Caton was part of this project. Jeet was also involved in this project for a little bit as well. This had a lot of different objectives. One main objective was to figure out how we could size the system, design a system in a way where we're controlling it to be able to provide the greatest amount of flexibility. One really great thing about thermal energy storage that I'm going to mention as well is the ability to downsize your system. So a lot of heat pump systems, a lot of HVAC systems currently are sized in a way where you're sizing to kind of peak load, right? So you just oversize the system. A lot of the year, you're not actually needing that much capacity, right? With a thermal energy storage system, you could take that peak value and maybe have 30% of it coming from 30% of the capacity coming from thermal energy storage, 70% coming from the air water heat pump, and that way you're not having to oversize your system like we've traditionally had to do. So a project we performed at FlexLab kind of revolved around these questions of how you would size a thermal energy storage system based on your goals in terms of flexibility or price responsiveness. So I'll try to kind of breeze through this a little bit, but kind of business as usual with no thermal energy storage is this point B here, which is you size your system to meet that peak load. But with thermal energy storage, you could theoretically downsize your system all the way to point A, where you still can provide the same amount of service, but now you have a certain amount of TES capacity that could help with that lacking capacity. The thing about this is you need to have more advanced controls to be able to kind of balance both resources, look at what the price signal is coming up, potentially be able to predict the load. And this is where something like water predictive control can shine, right? So we conducted a test in FlexLab where we had a hard run the loop approach. We modeled a thermal energy storage integrated system in Modelica. We compiled it into something called a functional mockup unit, and then created a hard run the loop interface where we're actually able to match the output of the model into the water loop at FlexLab, and then run the simulations that way, get data from FlexLab based on what's going on at the plant level, right? So we ran two scenarios, one where the system just responded to a price. So overnight it charges, and then when that price signal hits, or that high price signal hits, it will just discharge to the thermal energy storage. The model predictive control can actually look ahead at the price, look ahead at the thermal load coming up, and make a decision on how it wants to shift its load that way. This was supposed to be a cooling test. We ended up having to wait until December to run it, which was unfortunate, but that's just what it is. So the system we sized was something for a summer test, and ended up being a little oversized for what we were trying to do. So basically what the MPC is doing here on the orange line here is knowing that it can kind of predict the thermal load ahead of time, it actually decides to discharge the thermal energy storage earlier than when the price signal hits as compared to the baseline, right? So what that happens is now all of a sudden you have to charge more overnight, but it knows that the price signal is low there, so it doesn't matter. It'll charge overnight a little more to then discharge earlier every time, right? So given this, you're always going to have an ability, especially when you don't have to kind of meet these peak loads, to shift load and reduce costs even more than you would with just a baseline price responsive logic. So yes, go ahead.
So this is experimental data, not simulated.
So yes, so it's kind of both. So the results you're seeing here are all simulated data, yes. But the input to this, the input to what's going on to the model is actually coming from real data from FlexLab. So that's kind of the hardware in the loop approach, right? Where you're able to emulate the conditions in the model into FlexLab, and the kind of return air conditions, the return water conditions coming from FlexLab are put back into the model to emulate kind of what would happen. So yes, this data is simulated, but it's using FlexLab data to determine how it's operating in its current state.
And so
Yeah.
what phase change material was it based on?
This is based on a characterization study that was done by a couple of researchers at FlexLab using a phase change thermal energy storage technology called, a company called SunAmp. We had a couple of batteries donated to us. We characterized the systems, kind of peeked inside, wink, wink, and we're able to actually build a physical model and characterize it based on different scenarios of flow and temperature tests to create a model in Modelica.
So were you trying to load shift cooling or heating?
In this case, it was cooling.
And so earlier, you said you might have two different phase change materials, one for a low temperature and one for a high temperature. So this was a specific phase change material designed for that kind of shift.
Exactly. Yeah, for cooling shifting. Yes. Summer shifting.
Paraffin?
I'm not sure if it was paraffin. I think it's salt hydrate. I'm not a chemist, so I don't know what any of this stuff means. But it changes phase at certain temperatures. That's all I know. But anyway, let's kind of move on. I think I'm kind of over time here. Anyway, I think this is just showing that we were able to kind of reduce HVAC costs by 19%, given this MPC that we tested in FlexLab. And not only are we kind of simulating this, we're also building a prototype of a thermal energy storage integrated system. Dr. Kissick, in this case, we do have two temperature PCMs, one at 11 Celsius, another one at 48 Celsius. And we're able to shift for heating loads and shift for cooling loads if need be. And as part of CalFlex, we're taking that standardized price signal and developing a pricing logic for this prototype as well. So I think that's it. That's kind of my summary slides. Heat pumps, thermal energy storage, the future put together. They're going to allow us to kind of decarbonize a little more deeply, shift loads based on the need for grid services, auto predictive control. If you're able to kind of you have the training to build something like that. Is going to provide even more optimized operation of these systems. Yeah, that's kind of it. Thanks, guys. Appreciate it. Sorry about that, Marco. It kind of went way over, but so I'll let you take over.
No problem. Do we want to do question and answer at the end or now or?
It's up to you guys.
I think if the presentations would be similar, then we could probably do it at the end.
I think they're vastly different, right, Marco?
Who knows? We'll see.
Yeah, I'll say you go for it, and we can answer questions.
Yeah, I need to find the presentation now because it's gone. Okay, the other one. Okay. Back to me. So also, I just want to say that Armando's been modest there because he actually presented to the Secretary of Energy, and he got also an award for doing a great job. So he had a sneak peek of the Secretary visiting, and he presented some of our work there. So that was awesome. So I don't see anybody. Is it possible to turn around the camera because I don't need to see the screen?
I think it follows, right? Is it on the conference? It's just.
There are 13,000 of us here.
Oh wow, I am scared now. Oh, awesome. Okay, great. Well, thanks. Hi, everybody. My name is Marco Pritoni. I'm a former WCC PhD student, and now I work at LBNL. My presentation is kind of is going to talk about a little bit about me. It's going to talk about the big picture, and it's going to talk about a very specific single problem that I can address in 10 minutes. So we're happy to answer questions and kind of follow up with you guys. These are kind of sneak peeks of some of the works we're doing, but feel free to reach out afterwards. Okay, something about me. I flew in 2008 from a small town in a big valley that had a lot of agriculture in Italy to a small town that had a lot of agriculture in the US, Davis. And I followed my wife, who got a postdoc position at UC Davis, and I left my job. I was working in industry back in the days, and I moved here in the middle of the financial crisis. So I sent 350 resumes around, 0 jobs, and I had to reinvent myself in an energy guy. I was doing manufacturing before, and then suddenly I took a few classes at UC Davis, and then I met a professor who may be there, I don't see him, Alan Meyer, who I kind of knocked at his door and said, I'm an Italian engineer, I want to take your class, but I do not have any money. So he kind of laughed and he let me in, and he gave me an opportunity to kind of study energy efficiency. I volunteered a bunch of the what was called Energy Efficiency Center back in the days, and I got kind of introduced to many people, and then I got a job at the lab for about a year. And when I was done, I had an opportunity to start a PhD, and I started in mechanical engineering at WCC. So that was an amazing 6 years of my life where I kind of explored a lot of different things, collaborating with different campuses. And I got my master's, then my PhD, and then I finished in 2016, and I got rehired at the lab now as a scientist. And I kept working with a lot of people in this area and in the different campuses with different collaborations. So my experience of this area, I was where you are now a few years ago, and it's been kind of a struggle, but also very exciting. And working at the lab is like a unique place because you got to do different things every day. So you can go crazy, but also it's kind of very rewarding because there's always novelty. There's always, you can be like very entrepreneurial and come up with ideas, propose them, pitch them, get them funded. So it's not a boring place at all. And we also do a lot of useful work and that has impact on society. So I ended up now having a pretty large group. That's not kind of all my team on the left. It's part of the people that I co-own, meaning that we're all very matrixed. So I'm supervisor of a few of these. And we had a lot of former students that went through the system, some of which were UCD graduates that we hired, and then they kind of went on doing grad school, etc. And so I hope we get some of you or some of your colleagues in the future and to experience what it is working at the lab. We have a lot of internships and other opportunities. That was a bit about me. Big picture, Armando kind of give already a pretty good idea of the need for decarbonization. Climate change is rampant, it's rapid and intensifying. Buildings, which is what we work on, represent 30% of the emissions. Buildings are terrible. As you can see there, this is a thermal image, and it shows that these buildings are very leaky and they let go a lot of heat and a lot of air. And so it would be great if we could replace them and build new buildings. But the rate of replacement of buildings is actually 1% a year, and we can't afford 100 years or 50 years to get to a better stock of buildings. So a great opportunity instead of kind of just replacing envelope, which is what's around your walls and your windows, which is very expensive to do, is using controls. Controls give you both the ability to change the efficiency of the system, especially if they're operated not particularly well, which is the case in most of the buildings, and to become flexible. This is important because, as Armando was saying before, we went from a scenario where the users and the demand was asking the grid to give them energy, to a system where now you have renewable energy that are not controllable, but you still want to use them because they're good for decarbonization. And so you need the flexibility to move from the supply side to the demand side. So to have flexibility in buildings, you always need controls. Controls are a set of things. Armando talked about MPC, which is what's called here optimal model-based control. You can have rule-based controls. They're pretty efficient and pretty good. And you can have the more modern AI-based optimization. We also talk about analytics. Analytics are basically analysis of the data that can be done either in real time or after you collected the data. And they are typically used by people to analyze what's wrong with the system and fix it. In the future, there's also going to be sort of bots or artificial intelligence that look at the data and produce changes, but more in general, this is for people. So I want to talk about something slightly different. So Armando really touched on a lot of interesting areas of research on the sort of more mechanical engineering side. So like doing experiments, building prototypes, and figuring out what is the technology for the future. But it didn't quite touch on the concept of scalability. So I learned this working with a lot of computer scientists. They always talk about abstractions and generalizations and things that could be moved from n equal 1 to n equal 1 million. So the internet is an example of that. And to enable these these controls to be scaled up, you need various things. You need interoperability in digitization. Digitization just means that things have to be machine readable as opposed to a Word document with instruction on how a system should work, which is what we do right now. And they should be built to incorporate human factors in the system. So the controls are now, there's a lot of literature on optimal controls, and they're all great. But where the challenge is how do we scale these controls from one building, one system to the whole, stock of existing buildings. You can see here also on the right the thermostat, and some of you may be familiar with, that was developed at UC Davis and that's still running. So again, to the concept of portability and scalability. This is again if you think about smartphones, everybody is familiar with those. You develop an app, Somebody spent 6 months in doing that, and then you click a button, and your phone downloads it, and you have the app running on 4 million phones. It takes 4.3 years of machine time, 6 months of human time, and it's done. What we do in buildings right now is we do one smart building. It takes 6 months to implement, and then we do another building, and it takes another 6 months. So Biden administration had the goals of retrofitting 4 million buildings, and that would take about 2 million years. So this is not a sustainable model. How do we change this? And this is where I get from the general picture to a specific problem that we address in some of our research. This is about a specific case of interoperability. So you guys are not familiar with building automation systems for large buildings, but this is a very important key to scale things up. Large buildings cover more or less 50% of the square footage in the United States, commercial buildings, and they account for kind of proportional emissions. And they are controlled by systems that were designed and built in the 80s. And they're terrible. And the way they're set up and sort of initialized, if you want, a computer science term, is that there's a guy going into the building and programming manually things in each building. And so what you do when you interface with these buildings is you look at the data, and there's like everything is custom. They use naming conventions for like points and sensors. They're all over the place, and nothing is standardized. And so one of the sort of approaches that we take to standardize this is called semantic interoperability. So an example of how a building looks like is on the right. You see a long label, and that is kind of how you recognize what that sensor means. In this case, the site is Soda Hall in Berkeley. There's an air handling unit. It refers to a specific zone with an ID, and it's a sensor name. Those are so not standardized that we went into 3 buildings, and we found about 25 ways of coding the same type of sensor. And so they're not machine readable. They're not even understandable. So there was a lot of research a few years ago on machine learning, and still going on AI. But one of the challenges that many people in other fields, not necessarily in buildings, found is that the meaning of the data that is underneath is very important to run AI. And this is kind of the same problem mapped to building. If you don't know what the data means, you can't quite do anything with it. So the semantic interoperability, which is kind of the idea of knowing the meaning of the data, is a thing where we're addressing through what's called semantic models. Semantics models are a way of representing the structure of the data. So for example, there's a VAV box, which is like a piece of equipment which is connected to another air handling unit, which is another piece of equipment through a duct. That information can be codified in a graph. The graph represents both the kind of relationship with the different systems and the role of each component. And by using this graph, as you can see, there's a graph on the left that represents that building. You can pass it to a machine, and a machine is capable of ingesting it and understanding it and querying it and finding information in the system, differently from looking at the label and trying to figure out what the hell that technician wrote when he wrote it. I don't have the time to go into the details here, but what we proved, and there's publications on this, is that if you have semantic models applied to many buildings, these are some of these are UC Davis buildings that we kind of got the data from facilities and kind of scanned and put it in our kind of format. You can run the same application, the same lines of code on hundreds of buildings. And this is kind of revolutionary, because before you had a technician who had to code the same instructions on each building separately. And so this is the way we see the future moving forward, but it's still taking a while because industry is kind of resistant to to this kind of change. So a lot of details in this slide. Happy to follow up with you guys on what it means and what we did. And if you're interested in this type of research, we're open to discuss with you. What you can also do with semantic models is linking different pieces. So this is ASHRAE, is the organization of kind of engineers for buildings, energy, and other services. ASHRAE creates standards. And so a semantic model is capable of linking the meaning of the data. There's a standard that we're working on called 223P with the communication protocols to send information around the building in the control system to the control logic. All these are now or in the near future going to be able to be expressed as machine readable information, and it will kind of advance industry forward and academia too. So in essence, what we want to try and do is move away from the picture on the left, which is what we had before, and moving towards a picture that is more similar to what we do with smartphone. Obviously, a building is a much more complex and diverse system as opposed to, you know, a phone to another phone. But the idea is the same: develop the application that generalizes some of the logic, some of the concept, and then configure the application on the big building as opposed to rewrite it from scratch. So Armando and I have been talking about research. Some of you are involved in research that is much more theoretical than this. What we do at the lab, and specifically, you know, what I presented here, is really like in a spectrum from basic research to standard development, covering quite a kind of a spectrum of things that we call applied research. We call the deployment and the demonstration, which is basically just proving in the field that what you think it was true is actually true. Then transfer of the technology to industry, and then standard development. So we do all this sort of things. And at the bottom, you see some of the activities. Again, a lot of information here. CalFlex Hub was mentioned before by Armando, but in general, we have a lot of interest from DOE and from other funding agencies to moving away from how do we prove the best algorithm to how do we decarbonize building now. And I think this is a very important change, and it's something that you guys should think about in the future, because unless you're professors or like pure academics, you want to make an impact in life of people in your in your lifetime, and this is also necessary to avoid catastrophe. So hopefully you'll be interested in this and hopefully join us in the battle against climate change and sort of work in a spectrum of these things, even on the industry side, on kind of moving forward the building sector or whatever sector you're going to work on. So kind of some final remark. It's essential to tackle buildings for decarbonization. They're like about a third of the problem. Designing new building is not enough. We want to do controls because they're effective and you can implement them very quickly. To deploy them at scale, you need interoperability, you need human considerations, and you need a lot of interdisciplinary work. Our team, meaning LBNL, is working on a lot of these areas, and Armando presented a few, I presented some more. Many other people at LBNL are developing little pieces of the puzzle. Yeah, and so we really want to cover everything, because doing pure academic research is not enough, and it's not enough just doing, business as usual in industry. That's it. Thank you.
Yes, Dr. Casillas.
And Marco, I have a question, a comment question. First of all, the problem you identified about lack of nomenclature and custom programming of all these things is, in my experience, gigantic. It completely, you can go into a building and spend an infinite amount of time just trying to figure out what these sensors are. So I think you're working in a really important area. My second question is then how is this going to be implemented, right? If there's some standardized way, you know, possibly, you know, visually with graphs and stuff like this, how is this going to make its way into the actual building energy management systems, you know, in less than 40 years?
Yeah, so great question. I wish I had the you know absolute answer. I can tell you what we're doing. So we're working with ASHRAE and all the industry partners, so all the control vendors and all the analytics vendors, in a collaborative fashion to figure out what is an acceptable standard. And then we have different pathways for adoption. One of which I think it's probably the most short term. There's a lot of now products that do like fault detection and diagnostic. And those are typically software layers on top of the building automation system. And so they already exist. And they already have a way of kind of codifying knowledge through some either a graph or another structure that is less idiotic than a string. And so we're working with them so they can adopt the standard, and we can use the standard as a way of simplifying things in the future. So one of the vision is I am a vendor of an air handling unit. My air handling unit has a specific configuration, and I should be able to have a stub of how this thing is set up that I can give to, you know, the installer. When they install the system, they put all the stubs together. It creates the model of the system, and anybody else who needs to write an application just reads that model. So again, it on existing buildings, it's gonna take a while to get there. There are alternative methods. So there's like either semi-manual ways of mapping buildings to these sort of ontologies or graphs that currently have been used, and they're not great, but instead of 2 days or 3 days to code something, it takes, you know, a few hours. And there are machine learning approaches by which they kind of read the labels, so they kind of classify them. You can maybe ask a question to the facility manager, like, does this look like a sensor of this type? Yes, that takes gets, you know, taken into account in the algorithm, and it kind of classifies progressively your system. So you go from, you know, what you had to a new map, and that map should be used, you know, from now on to develop applications. So that's, you know, part of the vision.
So what usually happens next after this? Well, I think we're good to go, yeah.
Fantastic.
Well, Marco, thanks for joining virtually, appreciate it.
Well, thanks. I wish I could come, but I have contractors here and other grants, as you know, Armando.
You're gonna miss lunch. That's what comes next.
It's pizza, so you're not missing much. You know, you're a pizza snob anyway.
You never know. Yeah, I mean, it's nice to see some, you know, faces that I know. Robbie, Peyton there. I don't know if I know everybody else there, but
Hey,
oh, Teresa, hi,
Fred.
That's pretty cool.
and Kelly, obviously. Also Alan in the back. Is that Alan?
Yeah, that's Alan back there.
Yeah, it's his fault if I'm here. So Armando, maybe you can, when you're there, you can understand, you know, who's doing what. It'd be, you know, great to reconnect this community. And
Yeah, definitely. Well, that's the hope.